So we continue with problem number 34. A grinding wheel is in the form of a uniform solid disc of radius 7 centimeter and mass 2 kilograms. It starts from rest and accelerates uniformly under the action of the constant torque of 0.6 Newton times meter that the motor exerts on the wheel. Question number A, our first question, how long does the wheel take to reach its final operating speed of 1,200 revolutions per minute? And second question, through how many revolutions does it turn while accelerating? So these are the two questions that we are going to solve. Let me go to the whiteboard. So let me write down the summary of the given again. So for the problem 34 we have a grinding wheel اللي هو الدولاب اللي كانوا يطحنوا فيه يستخدموه ليطحنوا فيه زمان. So it's modelized as a uniform solid disc. So let's write down. It's a uniform solid disc and it has the following properties. So the radius is given by 7 centimeter and its mass is given by 2 kilograms. This is it. It starts from rest and accelerates uniformly under the action of a constant torque of 0.6 newtons times meter. So don't forget that it accelerates uniformly. This is very important. What does it mean? It means that it will rotate under constant acceleration, angular acceleration. This is it, and I want to add something on this given is that the moment of inertia of a solid uniform solid disk is given by 1/2 mr squared, so it's half mr squared, which is usually in the given. بس نحن هون ما عطينا ولا problem moment of inertia لأنه عندنا التيبل بالchapter. Okay, so in question A we are asked about how long does it take to reach its final operating speed of 1,200 revolution per minute. يعني قد ايه the time needed, let's say. فينا نقولها يا اما at what time t. So what is the time t? Let's say tf. How much is tf? Okay, for which omega tf it's given by 1,200 revolution per minute. That's the first question. And then in the second question we are asked about through how many revolutions does it turn while accelerating. قد ايه كم برمة عمل while accelerating لحتى يوصل لهيدي الأوميجا T final equals to 1,200 revolution per minute. So let's call it how much is delta theta. Right? So this is it. طيب كثير منيح. خلينا نشوف كيف بدنا نحله لهذا السؤال. بلش بأول وحدة بأول part. مطلوب مننا نجيب شو هي التايم TF, okay, for which omega T final is equal to 1,200 revolution. So if we know omega as a function of time, we can deduce how much is T final. But for this reason, we need to know the equation of omega as a function of time. And since here it says that the wheel, it accelerates uniformly under the action of the constant torque of 0.6 Newton times meter. هذا الشيء بيعني كذا شغله. أول شيء uniformly accelerating يعني it has a constant acceleration. وأكد لنا هالمعلومة لما قلنا إنه هو it's accelerating uniformly under the action of the constant torque of 0.6 Newton times meter. معناتها إنه the net torque acting on this object on this wheel هي given by tau net equals 0.6 Newton times meter. وهالتاو net هي constant. ونحن بنعرف إنه التاو net it's equal to I multiplied by alpha. فإذا التاو net هيدي constant معناتها إنه الألفا كمان is constant لأنه الI هو عبارة عن مجرد رقم. It's the moment of inertia which does not change as a function of time. So from here صار في عنا اثنين شغلتين بأكدوا لنا بالgiven إنه it has a uniform rotational motion أو بمعنى آخر uniformly accelerated rotational motion. And so we know already that omega as a function of time, it's given by alpha t plus omega 0, right? This is it. بس نحن بنعرف إنه الأوميجا 0 is equal to 0 لأنه هو قال it starts from rest. So already omega 0 is equal to 0. And so we can from here deduce that the time t final it's given by omega at the time t final divided by alpha. Now, the problem is that we don't know how much is alpha, right? But we know that tau net is equal to I alpha. We know tau net, it's equal to 0.6. Alpha is the unknown. I فينا نجيبها من خلال الإكسبريشن اللي هي half mr squared, given that we know what is m and what is r. So let's go ahead and we have to determine alpha. So let's determine alpha. Determine alpha from Newton's second law for rotation. We know that tau net is equal to I times alpha, right? And we know that I is equal to half mr squared. We just need to put all this information together, and so we end up with alpha as equal to tau net divided by I. So it's equal to 0.6 divided by بالنسبة للI ما نحطها بقيمتها تطلع معنا. So let's put it, it's half multiplied by the mass اللي هي 2 kilograms multiplied by the radius. The radius هو عبارة عن 7 centimeter, so it's 0.07 meter squared. And so we end up with alpha equals the value 122.4. No, let me just check. So it is 122.4 radian per second squared. radian per second squared. صار معنا الألفا ونحن معنا الأوميجا تي فاينل، بس بينقصنا أنه نقسمهم على بعضهم. So الأوميجا صارت عنا الألفا عفوا equals to 122.4 radian per second squared. ونحن بنعرف إن الأوميجا at T final it's equal to عطانا هو بالgiven 1200 revolution per minute. right. طيب بس نحن revolution per minute منا اليونت اللي عنا اياها للالفا، سو خلينا نعمل لها conversion ل radian per second squared. بالنسبه للريفوليوشن 1 revolution is equal to 2 pi radian، فبيطلع معنا 2 pi radian. 1 minute هي 3600 or just sorry هي it's 60 seconds، نحن مالنا بالhours so 60 seconds. And so we end up with the value. Okay, I didn't apply the value in here, so let's do it just right after. And so we end up with finally the time t final, it's given by, again, omega t final over alpha. So we end up with the value, so it's 1200 multiplied by 2 pi over 60, هيدي بالنسبة للأوميجا final, times 1 over 122.4. And so we end up with the value 1.03 seconds. So this is the time needed for the wheel to reach the speed of 1,200 revolutions per minute. So this is it. This is how we can determine omega. And it's quite easy. The basic equation اللي قلنا هي kinematic equation for a rotational motion under constant angular acceleration. وهول الايكويشنز بنعرفهم بنقدر نستخدمهم بشكل مباشر. تاني سؤال كان about the delta theta. How many revolutions the wheel does it turn while accelerating؟ يعني من التايم t 0 للتايم هيدا t final قد ايه delta theta؟ Okay, so again here we know already the basic equation that we are going to use. We know from the kinematic equations that theta as a function of time, it's given by half alpha t squared plus omega 0 t plus theta 0, right? And we are looking for the delta theta. Now let's see. The omega 0 هي equal to 0 لأنه it starts from rest, and the delta theta that we are looking for هي theta t final minus theta 0. تطلع معنا هي نفسها half times alpha times t squared, right? صار في عنا كل شيء. So this is delta theta we are looking at is equal to half multiplied by الألفا قيمتها 122.4 radian per second squared. والتايم هو جبناه قبل شوي t final 1 point. So delta theta t final in here 1.03 seconds. And so we end up with the value squared 64 64.9 radian. So بيطلع معنا قيمتها 64.9 radian. Now, if you want to express it in terms of revolutions, we have to define this value in radian by 2 pi لأنه one revolution هي 2 pi فلحتى نعرف delta theta is equal to 64.9 divided by 2 pi وبيطلع معنا value 10.3 revolutions. So this is the number that we get. We get the value delta theta given by 10.3 revolution. And again, this is it. This is how we use the kinematic equations to solve this kind of problems where we need to know information about the angular variables like alpha, omega, theta, etc. So this is it for this problem. Let's move on with another problem. We continue with problem 37. Let me just share my screen again. A block of mass M1 equals 2 kilograms and a block of mass M2 equals 6 kilograms. So as you can see, M1 and M2, they're connected by a massless string over a pulley in the shape of a solid disk having radius r equals 0.25 meters and mass m equals 10 kilograms. Now, these blocks are allowed to move on a fixed block wedge of an angle theta equals 30 degrees, as shown in the figure below. So this is the figure in here. M2 is on an inclined plane that is connected to a flat surface where M1 is sitting. Now, the coefficient of kinetic friction is 0.36 for both blocks. So both surfaces, they are not smooth. You have to draw free body diagrams of both blocks and of the pulley, and you have to determine A, the acceleration of the two blocks, and the tension in the string on both sides of the pulley. So here, as clearly stated in the question already, the acceleration of the two blocks, which means that M1 and M2, they are moving with the same acceleration. And the tensions in the string on both sides of the pulley. So we have the tension in this part of the string is different than the tension in this part of the string. And the pulley in this kind of problems in this chapter, it's not considered to be massless, and it has a mass that is different than 0. It's equal to 10 kilograms. So we cannot neglect any longer the rotational motion of the pulley. And in this problem, we are going to consider it in our discussion. So let's start with this problem, but let me move to the whiteboard. So let's start first by drawing the free body diagrams for this object. And to make it easy, or just easy for you to see each part, I will put them down just here, down each one aside. So let's start with the block 1. With the block M1, what do we have? So we have the following forces are acting. So look, I'll put here this block, here it is, and I will put the forces in blue. So again, we have nothing surprising for the weight. We have the normal acting on the block by the surface. So let's call them, this is N1. Of course, this is the weight M1G. We have, let's suppose that the system is moving downward. In other words, بما انه M2 is greater than M1, so let's assume that M2 is moving downward like that, and so this is A2, and M1 moves then to the right, so this is A1 basically. And if it's so, then على البلوك M1 بما انه في friction, فالفريكشن عم تكون عم بتعارض الموشن للM1, and so the friction is expected to be pointing to the left. So this is why here we will put F1 pointing to the left. This is the friction that we're going to call it F1 to say it's the friction between the block M1 and the surface. And the block M1 is also connected by the string, so this should be the tension T1. So this is it for the block M1. Now let's move on and then see what happens on the block M2. So for the block M2, the block M2 is on an inclined plane. So I'll just draw it like that on an inclined plane. And then let's draw again together the forces. So we will have the weight as a first force acting. We have also the normal exerted by the surface on the block M2. Since the block M2 is going downward, then in this case, the friction would be opposing the motion of the block M2, and so it's going to be upward with respect to the inclined plane. فال F2 راح تكون لفوق، وال M2 كمان is connected with the string on the other side of the pulley. So we have the tension T2 also acting on the block in the upward direction. Now, still بعد في شيء رابط ما بين البلوك M1 والبلوك M2. We have the pulley. And in this case, in this kind of exercises for this chapter, since the pulley, it says in the given that the pulley is in the shape of a solid disk having a radius r and the mass m, then we cannot neglect its motion. And we know that as long as this m2 is moving downward, the pulley is making rotation about its axis, اللي هو central axis اللي لها. And so if we just have a look at the pulley, هي البولي هون موجودة وعم تعمل روتيشن بالنسبة للبوينت اللي مارق بنصها. Okay, so if we want to draw the forces acting on this pulley, we will have at some point. So first of all, هون في الكورد اللي مواصلة على M1. So we'll have at this upper point the tension T1 اللي هي tangent على هالنقطة من الcircumference للبولي اللي هي in connection مع البلوك. يعني آخر نقطة ما بين السترينج وما بين البولي. And we have on the other side as well the tension T2. So كمان tension T2 it is like this. اللي هي connecting البولي مع البلوك 2 لتحت. And of course we have the weight وفي عنا النورمال. So خلينا نحط الويت بهالشكل هيدا لأنه واضح. This is mg. Okay, and we have the normal somehow passing through the axis of rotation. Okay, so راح ارسمها انا شوي بهالشكل هيدا، بس هي مبدئيا مش بالضروره تكون بهالشكل، هي حتكون along the axis of rotation. I'll just put n. Okay, let's put it like that. Oops, yeah. So let's put it like that, and let's put n in this way. And so let's move on. Now you have to determine in the part A, we have to determine the acceleration of the two blocks A. And in part B, we have to determine the tension in the string T1 and T2 on both sides of the string, of the pulley, pardon, in the string and both sides of the pulley. So let's start by just two main points in the discussion. The first one is that the two blocks, of course, they are moving with the same acceleration because the string is massless and it's inelastic. فبالتالي as long as the M2 is moving, M1 is moving as well, and the pulley is rotating. الثلاثة objects عم يتحركوا بنفس الوقت مع بعضهم بنفس الطريقة لأنه الكورد منا elastic. So this is why A of the block 1 is equal to A of the block 2 in magnitude. And we have both tensions in the string from one side and the other side of the pulley. So since we are looking for an acceleration and the force, the only equation that gives access to the forces, like in this case in هنا T1 with 2 هنا internal forces على system ككل, we have to consider the Newton's second law. And so let's apply Newton's second law for each part of the system. So we're going to consider part 1 اللي هي البلوك M1, part 2 اللي هي البولي, and part 3 for the block M2. So let's start for the block M1. So for the block M1, we have the following. Sum of external forces. So we have F1. رح أبلش من اليمين انطلاقاً على الشمال. So F1 plus N1 plus M1G plus T1 is equal to M1 times A1. And don't forget that A1 is pointing to the right. So this is A1. Now I will consider in each case the direction للA هي to be the positive direction, okay? أو إذا بدكم فينا ناخذ الX axis والY axis عموما، بس أنا بفضل ناخذ directional acceleration وهيك بنشتغل على أساسها. So we will have two projections basically من هون على الX على هيدا هون على البلوك M1 في عنا الX والY axis. So we end up with, so let's just take them حتى ما نفوت ب ما نحط شيء مش كاتبينه. Along the x-axis, what we will have? So minus F1 plus T1 is equal to M1 times A. لأنه الماgnitude لل A1 هي A. So this is along the X axis. And along the Y axis, we will have the following. Plus N1 minus M1G is equal to 0. Of course, because there is no motion along the Y axis. So we end up with N1 equals M1 times G. And from the first equation إذا بنحط كل شيء بقيمته بنحط هيدي بقلب أول equation بيطلع معنا minus mu1 N1 plus T1 equals, or given that F1 is equal to M1 mu1, so بما إنه F1 is equal to mu1 times N1 يعني هي equals mu1 times M1 times G. فبيطلع معنا بالأخير بنحطها بقيمتها بالإيكويشن we end up with minus 7.06 plus T1 is equal to M1 times A اللي هي 2 times A. And so this is the first equation that we can get from the from applying Newton's second law on the block M1. طيب رح نروح هلا على البلوك M2 وبعدين برجع على البولي. Okay, so for the block M2 what do we have again? So we have F2 plus T2 plus N2 plus M2G. This is the sum of external forces acting on the block. M2 is equal to M2 times A2. So again here what we are going to do is that we're going to take this, the X and the Y axis. بهالحالة حيكونوا شوي مختلفين لأنه حناخد ال X axis to be in the direction of motion. ما ننسى إنه بهالحالة هون let's call them X prime and Y prime. وما بدنا ننسى إنه البلوك M2 is moving downward بهالشكل هيدا. هيدي ال A2. So أخذنا ال X prime in the same direction as A2. And now all what we need to do is to make the projection. So شو بيطلع معنا؟ بالنسبة على ال Y prime axis يعني على ال vertical هيطلع معنا plus N2 minus M2G. هيدا هو الانجل هو theta angle هون. Let me just write it down. So هون هيدا الانجل هو نفسه الانجل theta. So بيطلع معنا minus M2G cosine theta is equal to 0. So plus N2 minus M2G cosine theta is equal to 0 as long as there is no motion along the Y prime axis. So we make the now the projection along the X prime axis, and so we end up with the X prime اتجاه ال A2 وال F2 وال T2 هن بعكس اتجاهه. ففي end up with minus F2 minus T2. So we end up with minus F2 minus T2. بس هون شو في عنا بعد؟ في عنا ال M2G عندها كمان projection على ال X prime لأنه ال M2G هون عندها projection على ال Y axis وعلى ال X axis. So you end up with plus M2G times sine theta equals M2 times A لأنه هون الماgnitude لل A2 كمان هي عبارة عن A. So if we use all the expressions هون بيطلع معنا minus mu2 times N2 وال N2 هي M2G cosine theta minus T2 plus M2 times G times sine theta is equal to M2 times A. Since everything is known, the mu is known, the mu2, the M2, the G, theta, everything is known. So if we make the numerical application, we end up with the following expression. So minus 18.32 minus T2 plus 29.4 is equal to 6 times A. If you just reduce the terms in here, you end up with 11.08 minus T2 is equal to 6 times A. And so this is the equation number 2 that we get from the from applying the block, it's Newton's second law on the block M2, right? At this point, we still cannot determine the value of A, of the acceleration of the two blocks, because we have two equations. So let's call this equation number 1 and this equation number 2. So we have two equations with three unknown, T1, T2, and A. And this is not possible. We cannot solve two equations with three unknown. We need one more equation. الايكويشن اللي ناقصه هي نيوتن's second law applied على البولي. بس بهالحاله we will not apply Newton's second law in the standard forms اللي هي standard formula هي sum of F equals ma. بس رح نطبق Newton's second law for the rotation اللي هي sum of tau is equal to I times alpha. And so let's do it in here. So now let's apply Newton's second law for the pulley. For the pulley, we will have the following. So tau net, our sum of tau equals I alpha. And so here we have four forces acting. I will call them, so tau 1 for the tension 1 plus tau 2 for the tension 2 plus tau g اللي هي the torque due to the gravitational force plus tau n, I will call it for the normal n. All of this is equal to I multiplied by alpha, where I is the moment of inertia of this pulley, and the pulley is taken to be a solid uniform disk, so we know what is the moment of inertia. Now, first of all, the weight of the pulley, it passes through its axis. The center of mass للpulley هو نفسه البوينت اللي مارق فيه الاكس of rotation. فبالتالي the contribution of the gravitational force to the torque is equal to 0 لانه مارقه بالاكسس. كمان النورمال n مارقه بالاكسس, so both these forces will not contribute to the rotational motion. Only T1 and T2 will have a contribution. And so let's now put in here the رح ارجع ارسم هون الpulley, and I will put the tension on it so that we can write down together the torques. So this is T1 as we have called them, اللي هو من هالجهه هي متصله بال M1. هون من هالجهه في عنا T2. Okay, now how much is tau 1 and tau 2? This is what we are going to define. So as we know, خلينا ناخذ السنتر, and the way we can determine tau 1 and tau 2 is that we have to draw the vector position of the point of application of these forces. R1 is perpendicular to tau 1. إذا بتيجوا بتستخدموا كمان the right hand rule, you will end up with R1 إصبعنا الكبير لفوق, T1 إصبعنا الثاني باتجاه الشمال, بيطلع معكم إنه tau 1 لفوق. So we will write down tau 1 pointing outward باتجاهكم برات الصفحة. أما بالنسبة للتاو 2 رح كمان نعمل نفس الشيء. We will draw R2. So R2 R2 هي الراديوس, T2 هي الفورس. R2 and T2 they are perpendicular, just like R1 and T1 they are perpendicular. And again we use our right hand rule. So R2 أول إصبع باتجاه ال R2, ثاني إصبع نزول باتجاه ال T2, بيطلع معنا ثالث إصبع لجوا. فإذا we can deduce that tau 2 it points inward لجوا بعكس التاو 1. So we can finally reduce إنه التاو 1 والتاو 2 هن مش بنفس اتجاه بعضهم. Now we have to choose one direction to be the direction of projection للتاو 1 and تاو 2. خلينا نشوف البولي كيف عم تبرم. البولي إذا كان البلوك 2 عم بينزل بهالاتجاه عم بشد الخيط, والام 1 عم تمشي بهالاتجاه معه, فبالتالي البولي we expect إنه هي عم تبرم بهالاتجاه هيدا, يعني clockwise. And if it is moving clockwise فإذا we can say إنه اتجاه الدورة يعني البرمة اللي لها هي لجوا الفيكتور. So we can put alpha pointing downward. And so this is it. Now if we want to make the projection of this equation اللي هي هون على الاكسس اللي هو inward أو outward, بدنا ننقي وحدة منهم to be positive والثانية to be negative. خلينا ناخذ الالفا to be positive على طول. طيب فاذا التاو 1 هي بعكس اتجاه الالفا, فحيطلع معي minus tau 1 plus tau 2 is equal to I alpha. اخذت اتجاه الالفا هو to be the positive direction, بيطلع معنا انه التاو 2 هي بنفس اتجاهها positive, اما التاو 1 بعكس اتجاهها فهي negative. قد ايه هي التاو 1؟ التاو 1 هي فاذا minus T1 multiplied by R plus tau 2 هي T2 multiplied by R اللي هو الراديوس تبع البولي is equal to I multiplied by alpha. So now we have again an equation in which we have بالنسبة للراديوس it's known بالنسبة للI it's a moment of inertia of a uniform disk اللي هي equal to half r squared كمان it's known. بس الألفا it's not known. So we end up with a new equation where we have a new unknown. So in principle there should be a problem if this is the case. But it's not the case. ليش؟ لأنه صحيح الألفا it's unknown بس ألفا it's related to A. نحن بنعرف إنه لما يبرم هيدا الدولاب اوكي والحبل يكون عم بشده البوينت مثل ما قلنا بالمره السابقه عم يمشي its acceleration it's given by the acceleration of the block A لانه هول النقطتين اللي هي على السيركمفرنس للويل والبلوك من ثاني جهه اللي هو البلوك M2 عم يمشوا نفس الديسبيسمنت بما انه هيدا الكورد it's not elastic and so therefore the A is equal to A to the block and A of this point is equal to R multiplied by alpha. So we know that alpha is equal to A over R on one side and we know that the moment of inertia of the disk is given by half mr squared on the other side. And now all what we need to do is to replace each of these two terms by their expressions in the equation. And so we end up with T2 minus T1, T2 minus T1 is equal to I alpha over R. So let's replace I alpha and I alpha by their expressions. شو بيطلع معنا؟ So بيطلع معنا الشيء التالي. So we end up with I هي half mr squared mr squared. Alpha is equal so A over R وفي عنا بعد 1 over R from previous equation. And so we end up with R squared من فوق مع R squared من تحت بيروحوا اثنيناتهم بيبقى عنا MA divided by 1 over 2 MA. So it's 1 over 2 M times A. والماس للبولي هي equal to 10 so we end up with 10 over 2 so we end up with 5A. And so finally we end up with a third equation given by T2 minus T1 is equal to 5A. So this is the third equation that gives a relation between T2 and T1 and A as well, of course. And so we end up now with three equations that all relates the variables T1, T2, and A together. And so we have three equations with three unknowns that we can now solve them. And if you just take all these three equations together, you will end up with, so T2 بنجيبها من equation number 2 بتطلع معنا T2 هي عبارة عن 11.08 minus 6A. So 11.08 minus 6A minus T1 بنجيبها من equation 1 بتطلع معنا عبارة عن 2A plus 7.06. That is equal to 5A. نشتغل شغلنا بيطلع معنا انه 4.02 is equal to 13 times A. And so we can deduce A equals to 4.02 divided by 13, 0.309 meters per second squared. And so this is the value of the acceleration we were looking for. هيدي كانت البارت A. So بالبارت A بنجيب part A 3 equations together بيطلع معنا هيدا. أما بالبارت B كان مطلوب نجيب شو هي T1 and T2. So now we go back to the equation 1 and 2. من equation 1 بيطلع معنا إنه T1 is equal to 2 times A plus 7.06 and we end up with the value 7.67 Newton. And from equation number 2 we can deduce the value of T2. So we end up with T2 equals 11.08 minus 6A, which gives the value 9.23 Newton. And so this is it. This is the value of T1, and this is the value of T2. And so using the Newton's second law for translation and for rotation applied on the three elements of the system, the block M1, block M2, and the pulley, we can deduce the expression and the values of the acceleration, the tension T1, and the tension T2. And so this is it for this problem as well.